Thank you, Brian, for the introduction. My research topic is towards automated compilation of electronic navigational charts, or in other words, how to generate electronic navigational charts at any given scale from the database. So save a lot of time, a lot of effort, and solving many related problems. So before the ENCs, where mariners used only paper chart for navigation, where they have to switch manually from one chart to the other. For sure, there were lots of overlapping between those charts and inconsistency. As we can see over here, many overlaps between the same scale, but this was hardly noted since they have to use only one chart at a time. And then after the paper chart, and this has caused some problems that we are still suffering from it right now, which I'll be talking about in a while. So after paper charts, there were raster charts. And raster charts are simply an electronic version of the paper chart. So what you see is what you get. As we can see over here, all the information are on the chart, and most of the chart are cluttered with lots of information, as you can see over here. So if you want to inquire one object like a buoy like that, all you see is QR, which is quick flashing red. Then the next step was the ENCs, the vector charts. So the ENCs totally rely on a vector database, and it's the electronic version of the map. So all types of information can be embedded within the ENC. As we can see over here, the same buoy, we can see all types of information, add whatever we need, like the light characteristics, construction, nominal range, everything. And that's the same for all other feature objects. But the problem is when we started, or most hydrographic offices, when they started to move from paper chart and raster chart to the ENCs, they did that by digitizing the paper chart. So we've inherited this coverage of the overlap that we've just seen on the previous slide. And this causes some problems that I'll be talking about in a while. So why is it important? ENCs, in July 2018, the IMO, which is the International Maritime Organization, has made EGDIS loaded with official ENCs mandatory board all regulated vessels. So all types of vessels have had to have an EGDIS system. An EGDIS is the electronic chart display and information system on board any vessel. So all these types of vessels has got to have an EGDIS system with ENCs loaded with it. That's why it is important right now. So we do have 6 bands of ENCs, as we can see over here on top of each other, starting from the overview, which is the least level of detail or the smallest scale, up to the berthing and harbor scale, which is the highest level of detail. According to the S57, which is the current standard by the IHO, there are larger and smaller limits for those bands. And there is an S101 standard by the IHO, which is the IHO is encouraging all hydrographic office to switch from the S57 to the S101, and that's another challenge. And all of these scales are related or associated to the radar standard range. So there are many challenges facing hydrographic offices and ENC producers, since it became possible to view all these scales on top of each other on the EGDIS display. As we can see over here in this image, on any bridge or wheelhouse on a vessel, the EGDIS machine is side by side to the radar, and the mariner will be able to see all these scales by zooming in and zooming out on top of each other, besides seeing number of ENC cells side by side. So if there is any inconsistency, this will be very obvious for the mariner. And he should be able to compare the image from the radar, the coastline, to the coast representation on the chart in order to navigate in foggy or in any situation. So that's why both are side by side like that. According to the worldwide ENC database, which is WEND, it states that there must be no overlapping whatsoever between data, between cells of the same navigational purpose. Only a small portion is acceptable. So as we can see over here, this is not the case. That's the east coast of the US. We have a lot of overlapping between the same scale and a lot of orientations, and that's because the paper chart of the source. And to give you a round figure, only in NOAA, there are more than 1,000 NOAA ENCs that they maintain on the US coastal water and the Great Lakes. So, and there are thousands others worldwide that have the same problem. So to give you an example of the inconsistency and edge matching at cell boundaries, what we see over here is 3 cells. So when I say cell, that's an ENC chart, and that's one EGDIS display. As we can see, cell 1, cell 2, and cell 3, and they are all the same scale, scale 4. But what we see over here is inconsistency in the contour, and over here the contour is missing between these 3 cells. So whenever a mariner sees something like that, that gives him poor confidence in the chart. And the confidence level for the mariner is very important. So he's always checking the confidence level, or at least once while navigating in a new area, to see the accuracy of the chart. So whenever he sees 6 stars like that, or 5 stars, that's high accuracy. And then the accuracy goes down, and whenever it goes down, that's a red flag for him. So whenever he sees some inconsistency like that, that means that the chart is not, or he has some confusion or some poor confidence in the chart. Another example over here is one navigational mark that is encoded differently on 2 ENCs. So not only the position is encoded differently, it's just like you see, the attribution of the beacon is also encoded differently, resulting in differing the symbolization of the mark. So that's also cause some confusion for the mariner. Over here, that's an EGDIS display. As we can see, there are 2 cells over here on one EGDIS display, and the northern cell has no 15-meter contour. So whenever the mariner would set the safety contour to 15 meters, in this case, as we can see over here, EGDIS will jump automatically to the next level of contours, which is 20 meters, and this would cause some problems, maybe a false alarm for the vessel. Another example over here, discontinuity in the contour and discontinuity on the boundaries, areas, depth areas. Over here, the northern cell has very generalized depth contour, and over here, a very detailed depth contour, and for sure this makes some confusion as well. So these are some examples of the problems from the inconsistency. Now I can give you an example of the current NOAA ENC coverage on the West Coast. You see the overlapping between the cells, and these are the coverage for the ENC. So as a result of that, there are too many scales, duplication of coverage, lacking uniformity and consistency, and most importantly, inconsistency and no smooth transition from scale to scale on EGDIS. Accordingly, in 2018, NOAA announced the scheming of their new ENC suite that will replace this current puzzle piece layout with a rectangular grid of ENCs providing a seamless tiled coverage. So that for sure will solve lots of problems, but the problem is that needs a lot of time and a lot of effort to be done, because most of it are done manually by professional cartographers for sure. So this is another example of the current electronic chart suite on the East Coast. It looks like that right now, where in the future, after the scheming, it will look much better just like that and solve a lot of problems. So the most important thing from this scheming, that it will reduce the number of current chart scales from 131, which is a huge number, to only 12 unique scales, 2 for each band of the 6 bands. Accordingly, each 16 cell, as we can see over here, will fit perfectly into the extent of the second or the next smaller scale. And over here, if we see the band 5, which is the high resolution band, this is band 4, going to look like that, and so on, band 3 and band 2, until if we have band 1 as well. Those cells will be square by the equator in lower latitude, and then will be rectangular when we go to higher latitude according to the distortion in the Mercator projection. So to give you just a view about the production and updating time that is needed, all these steps are needed or recommended by the IHO in order to produce an ENC at the end, starting from designing the production process, very detailed steps, capturing the data, validating and verifying the data until we have an ENC database. And some hydrographic offices until now, they don't have ENC database. They just use their sources to produce ENCs. And that's a long, very long, detailed process. So there are numbers of ENC or production of ENC, like a new one, a new edition, reissue, or update, and then it has to go through the RINC, the regional ENC center, then the distributor network, and finally it goes to the end user. And that's take a lot of time to be produced. And in case of an accident or an update that need to update the chart, it would have to take the same loop again until it reach the end user. So imagine we need to update the 6 bands on top of each other in any area if there is 6 bands or 4 or 5 bands. So that's a lot of work and a lot of time to be done. For sure, if the process is automated, that will save a lot of time. That's only a figure that shows the time required for NOAA to update their coverage, as we can see, but this is in 2019, so for sure this has been updated. Band 4 will be fulfilled by 2024, and then Band 5 after that will be completed at least 2 to 3 years after the completion of Band 4 in any area. So my proposed research can contribute to solving some of these related problems, hopefully. For the production updating time, costs and time required for producing multi-charts will be significantly reduced, and the inconsistency and edge matching between charts of the same hydrographic office. So hydrographic offices can have time, could steer their effort toward harmonizing the data on the boundaries or finish their coverage, because there are still many hydrographic offices that hasn't been yet covered their territorial water with ENCs. In the sounding and curves on the US charts, the task of transferring to the metric international system can be achieved faster and with reasonable efforts. And in the inconsistency in spatial geometry and attribute encoding, so this effect can be eliminated, since each scale-independent feature, like a beacon over here, will have only one position and one attribute encoded in a single database, and then after that, all the products will be according to the database. So after we've seen the research problems and the importance of the ENCs, my research main objective is the development of a framework or a model for the automated compilation of ENCs through scales with minimum human interference, or hopefully no interference for sure. That would be much better. So in other words, the research aimed to translate the current cartographic practice and theory into some algorithm that can iterate and cooperate to find the suitable chart representation for any given area at any given scale. The end goal, which would be sure cartography at the point of use. So if we have a database updated with the most updated geo features, then we can go to any area and pick it, and then we have chart for this. This is cartography at the point of use. So accordingly, the main research question would be, what are the possibilities and limitations of creating a workflow that can safely automate the implementation of generalizing rules for nautical chart? And safety, how to safely automate, this is very important because we have constraint on the nautical chart that I'll be talking about in a while. So over here, I'm trying to give an example of a real life situation in generalizing an ENC from band 4 to band 3 to band 2. So we're going from the high level of detail, going up from the approach to the coastal to the general. So this is band 4 ENC over here on the East Coast, where we have a group of islands, group A and group B and group C, and the main group of islands, group D. So let's see what happened by professional cartographers when they do the generalization. When we jump to band 3 over here, you can see that group A has been aggregated, simplified. Some of the rocks and the islands has been eliminated and collapsed to point. Also group B and C, lots of operators has been done over here. And this beacon, which is the main beacon for the area, has been maintained in band 3. That's the coastal band. And then if we go to the level, the next level, which is the general, less detail, small scale, then group A has been totally collapsed to points. Group B as well, maybe one point has been maintained for the beacon to be on land area, and the main group of island has been simplified. One of them has been collapsed. And as you can see over here, those two beacons has been totally eliminated on the 2 seconds. So according to the cartographic principles and specification, the professional cartographers use their experience to do this manually. So the main question, can we automate this process and have the same results or better results by means of a model? That's one of the main research questions for my research. So we need to define the cartographic generalization. What's the definition of cartographic generalization? According to the ICA, the International Cartographic Association. It's the selection and simplified representation of detail appropriate to the scale and or purpose of the map. So for digital generalization, there are three main questions that needs to be answered. Why we generalize, when to generalize, and how to generalize. So in order to answer the first question, which is why we generalize, the first pillar of the aim to answer this question. It contains three main elements: theoretical elements, application elements, and computation elements. So we need to understand how to reduce the complexity of the chart to maintain the spatial accuracy, the attribute accuracy. And what's the purpose of the map? What's the main purpose of the map? What's the scale appropriate to this purpose? And then what's the effective algorithm, the cost of the effective algorithm, and how to maximize the data reduction? How much can we do that? So by understanding those elements, we can answer the first question, which is why to generalize. Then the second question is when to generalize. So through cartometric evaluation, like geometric conditions, we need to understand what's the conflict between two feature objects. If a contour needs to move and then there is sounding over there, that's how we solve something. What's the complication, inconsistency? So all these conditions need to be understood. All the spatial measurements, like the density measurement, what's the acceptable density for a group of islands, how to the distribution measurement, the shape measurement. So all of these need to be understood as well. In addition to the transformation controls, like how to pick the right generalization operator to do selection, to do collapsing, and what's the best algorithm? Because for every operator, there is a number of algorithms that can do the job. So what's the best algorithm to do that? And what's the best parameter for that? So by knowing all of these conditions and controls, we can answer the question when to generalize. And finally, how to generalize. So for sure, we need to understand each specific generalization operator. What does it do to the data? What's the difference between simplifying a line and smoothing a line? How to merge a couple of objects. There are several ways of merging. When to collapse a polygon to a point. So those spatial transformation and those attribute transformation like classification and simplification need to be understood as well. And by that, we can answer the last question, which is how to generalize. Then there are three types of patch processing for modeling the overall generalization processes that was found in the literature. The first one is the condition action modeling. An identification of the object and relationship between objects is first performed in the structure recognition, and then based on the identified conditions, generalization algorithms are triggered in the execution phase. So that's the condition action modeling. But for sure, in nautical chart, there will be lots of conditions that need to be done. So that's a very long one. Human interaction modeling, as we can see from the name, it's based on sharing the workload between the computer and the human. So typically, the computer will carry out those tasks which can be performalized into algorithm, and the human will control the software. So that's another approach. And the last method is the constraint-based modeling, which I'll be implementing during my research. And in this method, the requirement that must be fulfilled in generalizing the map act as constraint to the generalization process. So as a consequence to that, the generalization solution must satisfy as many of the constraints as possible. And this would be the accepted result by respecting the generalization, the constraint of the model. Accordingly, there are two main aspects of generalization: model generalization, which is also known as database generalization, and cartographic generalization, which is also known as graphic generalization. So in database generalization, the generalization in the conceptual level of the data representation. So that's when you generalize. So if you have a primary model, we can have several databases generalized from the primary model. Whereas in the cartographic generalization, it's about the changes in the geometric shape of the feature. Accordingly, we have two classified operators according to this. So the main difference between the operators, the two categories, is that the model operators can be applied on a complete data set, on the whole database. Whereas the cartographic operators can only be applied if a cartographic conflict needed to be solved, which occurs only on a subset of feature type. To give an example that has been done successfully in the topographic domain, and that has been done in Swiss Topo. The Swiss Topo is the Federal Office of Topography in Switzerland that is responsible for creating the national topographic maps. So they were able to completely modernize their national map series, relying on a digital cartographic model, the DCM. So as we can see over here, they have two categories of the database, and from that they generalized their map according to the scale. So they used a combined star and ladder approach, which I'll be talking about in a while, what's the difference between them. So 2 star and 3 ladder in order to generalize their maps. And they did that successfully in the topographic domain. Another very interesting case study in Cadastar in the Netherlands, where a fully automated workflow was successfully implemented to compile the 1 to 50K map from the 1 to 10 database without any human interaction. So the complete generalization workflow over here was implemented within the model builder in ArcGIS, which is exactly what I'll be trying to do using the model builder in ArcGIS to do the model. So this workflow consists of 3 models. Each one has some submodel that are responsible for solving each specific generalization problem. So if we can see over here, this is the fully automated generalized map, the 1 to 50 map by the model, and this is the one interactively generalized by cartographers. And if we can compare, I know it's hard to see the difference, but there's a high correlation between both of them. So this was proven to be acceptable or be a good example in the Cadastar. So that has been done in the topographic domain or topographic maps. So until now in the marine or in the nautical charts, it hasn't been done completely because there are some constraints in the nautical chart that makes it different than the topographic map. We have 4 types of constraints that need to be respected for generalizing a nautical chart. 2 of them are hard constraint. They are considered hard constraint, like the safety constraint and legibility constraint. They have a high degree of importance and should be rarely violated during the generalization process. And a couple of soft constraints like the topology and the morphology that are considered more flexible. So to give an example about a safety constraint over here, if we have a vessel and this is the sea level, so, and this is for sure the seafloor, if we have a 3-meter peak and a 12-meter pit, so we have 10-meter contour over here and a 5-meter contour. So during generalization, this contour or this sounding can be removed. But this 3-meter peak should not be removed for safety of navigation. So the system should understand this as a constraint, as a hard constraint for safety of navigation. Another example, which is a very important one, in depth curve generalization for nautical chart. So if we have a depth curve like that, depth contour, so there is a deep area over here, that's the deep side, and that's the shallow side. So this tongue is shallow. In order to generalize this depth contour in normal ways, or maybe in topographic maps, then this would be the generalized contour, this dotted green curve. So in the topographic map, this would be accepted, but in the marine or the nautical maps, nautical chart, this would not be accepted because for safety of navigation. That's why, because this area over here, this tongue, it's shallow tongue, moves to the deep area. So this would give a violation for the safety, because a vessel might run aground over here for false representation of depth. So this is not accepted. So how we overcome this? There are several methods to generalize the depth contour. The snake method is one of them, the snake model, which is defined by a 2-dimension parametric curve, as we can see over here, on which the force is defined through an energy-like term, which is defined by the derivatives of that. So the total energy is the sum of the internal energy, which represent the smoothness of the curve, plus the external energy, which express the external constraint on the curve. So here, the external constraints are used to represent the shoal bias rule, such that when the external energy is minimized as much as we can, then the shoal bias rule has been satisfied. The results of that, we can see it over here. So this is the accepted generalized curve according to the safety constraint, not this dotted one. So as a result of that, all this yellow area that we see, which was already deep, has moved to the shallow side, and this for safety of navigation is accepted. And the system has moved this generalized curve due to the external constraint and push it to the deep side, and this is accepted. So that's a big difference, a huge difference between topographic maps and nautical charts. Another example is the island selection, how to select islands in generalization. So islands are considered one of the most important geofeatures in any nautical chart. Actually, some researchers claim that the structure recognition and the quality of islands generalization directly determine the quality of any chart. So the existing method for automatically selecting islands usually utilize the Voronoi diagram. And what's the Voronoi diagram? As we can see over here, it expresses the density of these points where the polygon element exactly represent the generated space of the point it claimed by mean of this equation. So Pi equal 1 over AVPI, where AVPI represent the area of the polygon correspond to the point Pi. So if these points represent islands, and we have 3 islands over here, very close to each other, and we have an isolated island over here. So the Voronoi diagram has some drawbacks, some disadvantage. In cartographic principles, the denser points should be eliminated first while generalizing. So according to the Voronoi diagram, this point will be eliminated first or removed, and these 3 will be maintained according to the Voronoi diagram, as you can see over here, the polygon size, which represent the density. So there is a new research by Zhang that represented something called the influence domain. So Zhang just presented a new method based on the competitive influence domain, simply by adding a buffer to each island or each point representing an island. So simply the influence domain is according to the island own attribute. So as we can see over here on this group of islands, each island has its own attribute, its own shape, its own area. If there is any facility on the island, an important beacon, just like the case over here, if the island is close to a navigational line, so all of these attributes affect the buffer of the influence domain circle. Then secondly, those islands with the largest area of influence domain are selected. Then the island with greater overlap are removed, and then finally several groups of islands are selected automatically. So this is also an interesting one that might be used during the model for selecting islands. So according to that, after seeing what has been done in the field of the topographic maps and in the nautical charts, we've solved several items separately, like sounding selection, and for sure sounding selection lots of work has been done, island selection, depth curve generalization. My research workflow, I'm proposing to do 4 main steps. The first step is geoprocessing modeling with the ArcGIS model builder. So the main models will be created in ArcGIS model builder, then convert the model to Python script if we need to modify anything, and then batch processing with the Python script. And then finally, the most important one is the quality assurance by comparing the result of the model to the available ENCs in the study area or in any area that I will try to implement the model on it. And for sure, I will need some help from maybe the MCD in NOAA or anyone to look at the model and look at the result of the model to compare it with the available ENCs. So in order to pick the geofeature objects for my research, the ENC world has more than 160 geofeature objects. So for sure, I've picked some of them to prove the concept. And if I prove the concept that it's applicable on these geofeature objects, then we can imply it on the rest of them. In any ENC, there are 2 groups of geofeature objects. Group 1, which is also called the skin of the earth, has 7 feature objects, 7 geofeature objects. As we can see over here, land areas, depth areas, any dredge area, if there is any in the chart, unsurveyed areas, in addition to floating dock, pontoons, and hulks. So those are the 7 feature objects that represent the base of any ENC and should be without any overlap or gaps between them. And then the rest of the geofeature objects, all of them is group 2. So I've selected about 5 of them that are closely related to those 7. The coastline with the 2 types of coastline, the artificial coastline and the natural, depth contours and soundings, and aids to navigation. So those are the 12 feature objects that I've selected for this research. The database for this research is the NOAA Nautical Information System, the NIS. And the NIS is a multi-scale geospatial database repository for all current NOAA nautical charts, utilizing the Esri ArcGIS software. It's compiled of the nautical feature dataset, group of point objects like soundings, like wrecks, like aids to navigation, lines like depth contours, coastline, and polygons like land areas and depth areas and so on. So that's the nautical feature dataset. And then some nautical support table, and these perform a variety of functions like lookup tables, other database management function. And finally, a group of standalone feature classes. So these are the NIS, that's the database of my research. And we have several layers of level of detail in the NIS for the data. What's the sources for that? A lot of sources. The hydrographic data comes from the Hydrographic Survey Division, the geodetic control and shoreline from the NGS, all the channel data comes from the Army Corps of Engineers, and aids to navigation from the Coast Guard. So all these data goes to the MCD, where they do the compilation, and then the chart is the final product goes out from the MCD. So after picking the geofeature objects for my research, I have to design the conceptual architecture. So as mentioned before, there are two main generalization techniques. The ladder approach, which is an incremental fashion where the data set at each scale is a generalization of the previous one. So from the NIS, the highest level of detail is extracted for the area of interest, and then generalization rules will be set for extracting the next level from the previous one, for generalizing the next level from the previous one. Whereas the star approach, all the scale is derived, all the new generalized scale are derived directly from the highest level of detail from the NIS, and for sure, a set of generalization rules for each step. So those two approaches will be tested and will be tried in the model to figure out the best one of them, and maybe using a hybrid system, just like the one that was done in Swiss Topo. And I'm going to show you a brief result or a comparison between the two approaches at the end of this. So after choosing the 12 feature objects, each one of them should be assigned to an agent. So the main idea behind using an agent modeling is that each feature can act as an active and autonomous object or an agent that works on satisfying the constraint or the goals to achieve the optimal rendering at the target scale. So there are 3 levels of agents: macro agent, meso agent, and micro agent. So the macro agent controls the meso agent, and the meso agent contains the micro agent. To give an example, the coastline can be represented as a macro agent. So the first thing is to generalize the coastline with the 2 types of the coastline, the artificial coastline and the natural coastline. Then the land area will follow with no gaps whatsoever between land area and coastline. So the coastline controls the land area. And then the land area contains aid to navigation, like lighthouse or a beacon. So this is controlled or contained by the land area. So if we eliminate the land area, an island, then the lighthouse will be also removed, unless it's dominant to navigation. So it has to be maintained. So the land area has to be maintained as well. So there are lots of relations between the agents, and hopefully all of them will be assigned agents. And the agent has a life cycle. So once an agent is activated, as we can see over here, it goes through an iterative process, trying out different plans and evaluating associated constraint for possible violation, until the best solution has been found, where it will be saved, and we go on. So that's the life cycle of an agent. Then the study area. The study area was selected in the West Coast, the Puget Sound area, Port of Townsend in Washington in the West Coast. As we can see over here, that's the current coverage of the study area. Lots of overlaps, as we can see, but it hasn't been reschemed yet. But the current coverage is very thorough and seamless and would provide a good control for the automated output. So I can compare between the output of the model and the available ENCs in the area. And this is how it's going to look like after the rescheming according to NOAA. It hasn't been reschemed yet, but this will be the final product in the same area. So in the NIS, for the study area, we have 3 levels of details. As mentioned before, we have the 20K, the 40K, and the 80K on top of each other. As we can see, this is only the land area and the coastline. And we have 3 levels of ENCs, band 5, band 4, and band 3. As we can see over here, that's the M cover for each ENC. Then to design the general layout model, after figure out the process and the agents, now I'm going to be using each model to deal with the specific geofeature object, or at least a couple of them sharing the same geometry or the same S57 attribute. So I'm proposing the first model to deal with the coastline, the 2 different types of coastline, then the land area, then the depth area, and so on until sounding selection. And the final result, as we can see, will be the combination from the points or lines and polygons. So each one of them will be specifically dedicated to polygons, to like land areas, to depth areas, polygons as well. And then at the end will be combined together. A very important question over here, which I'll be answering it during the research. I don't know yet the answer to this question. Is it going to be sequentially or simultaneously? So am I going to wait until this model finish and then go to the other one and then the other one, or everything will be run simultaneously until I have the final result? This is a question that I need to answer during my research. Very important step is extracting the generalization rules and set the constraints. In order to the system, generalization system, to understand this, I need to, first of all, extract the generalization from the available documentation and then set the constraint and then translate this to an understandable format by the generalization system. So in order to extract the specification, this flow chart over here show how I'm going to do that, starting from the available documentation, which is the IHO S4 and the NOAA Nautical Chart Manual. And there are other documentation, but these are the 2 main ones. So is it possible to extract the specification? If yes, then proceed. If no, then create some specification accordingly. Then the next step, is there a tool in ArcMap to implement this specification? If yes, then it's a go. If no, then modify it in Python. And then finally, is it possible to execute this specification? If yes, then that's the goal, execute. If no, then go back to Python, modify, and keep going until to describe the possible solution at the end. So the key to start describing and formulating this specification is understanding the purpose of each scale, as mentioned before. So according to the IALA, there are 3 phases of navigation: the ocean navigation or the open water navigation, and 2 associated ENC bands, with that the overview and the general, and then the coastal navigation, and then restricted water navigation. And associated to that is the radar range for each one of them. And why is the radar range important? So according to the IHO S4, as mentioned before, the coast representation on the chart should be adequate enough to compare with the radar image for operation like blind pilotage or radar fixing. So in case of a foggy day, the mariner should be able to compare the image from the radar to the image of the coast representation from the chart in order to safely navigate. So according to the Bowditch, there are 2 types of resolution: the bearing resolution, which should be better than 2.5 degrees, and the range resolution, which should be better than 50 meters. So this means that if we have 2 targets more than 50 meters, we have to differentiate between the 2 of them. So relying on the bearing resolution, using this equation, which is sine the bearing resolution multiplied by the radar range in meter for the associated scale, this should be less than the level of detail in meter. And what do I need the level of detail for? For generalizing the coastline, or that's the parameter that should be fed in the algorithm to generalize. So using this equation, the level of detail, it represents this curve over here, the blue one, which was found to be very shallow or low resolution. So there is another approach by Tobler, and Tobler represented a theory that the size of the smallest detectable feature should be twice that of the resolution. So relying on that, this is the figures for that, give us this curve, the orange one, which is very fine or very high resolution to be used. So I'm proposing over here a hybrid approach that can be implemented by using the values of the level of detail, that Sochar work approach, and assuming it the smallest detectable feature, then using half of it. So this gives us this curve over here that I can use for generalizing the coastline or the land area during this research. And this for sure can be adjusted during research. So to give you an example on the specification that was extracted from the available documentation and should be translated to the system. So over here, if we have a construction or a pier smaller than 0.8 millimeter to the scale, which means in scale 1 to 10 is 8 meter, 1 to 80K, 64 meters. So if both direction for a construction or a polygon or a jetty is less than 0.8 millimeter, then this should collapse to a point while generalizing. Whereas if one of them is greater than 0.8 millimeter, then it should collapse to a line. So that's an example of a specification. Another one, topology specification example, it says that the coastline should coincide with the land area. So if we have a coastline like that, then the land area should follow with no gaps whatsoever. And then if we have a landmark like that, a beacon or a lighthouse, and we can select this by this algorithm by selecting from the aids of navigation from the NIS, and then on land, and if it's a beacon shape or landmark with lights, so we can select all of these. And then when we start generalizing, this is not accepted because we have to respect the land area and respect the landmark or the lighthouse over here during generalization. So the final accepted land area should be something like that, and the system should understand this as well. Another example, the last one, for merging islands, it states that the island will be merged to the coastline or the land area in case the geodesic distance are less than 0.8 millimeter again to the scale. So in scale 1 to 80, for instance, 1 to 80K should be, if you have the distance to the island less than 64 meters, that's the tolerance to the scale. So while generalizing, this island should be merged to the mainland, and this would be the final accepted land area. So I'm not expecting you for sure to read these tables, but I'm just showing you how to translate this specification into an understandable format by the system. So this how to translate the constraint to understandable format by the generalization system. Over here, for instance, the constraint type for each geometry, for line contours, for areas. So lines move only toward the deep area. So this is safety constraint, morphology constraint, topology constraint. That's on one object. What about two objects and then a group of objects? So for each geofeature object, there will be a table, a very detailed table like that to define the types of constraint. And then over here, what's the action needed that need to be done? What's the condition to be respected? And the importance of this action for each polygon or a two polygon or a group of polygons. So this is how I'm proposing that I'll translate this by this template, translating this constraint into an understandable language by the system. Over here as well, I'm not expecting you to read this. This is how I start the workflow, the flow chart for the workflow, what I need to do from the model, the coastline and the land area, extract them from the NIS. So the final model would be something very detailed like that. And over here within the model, I can have several sub-models. Each one of them can iterate through the database to extract the highest level of detail and then start applying the operators until I have the final product that I need. And this is just an example, a small portion of the model. This model, for example, show how I can compare between the ladder approach versus the star approach for land area. And I'm going to show you the results in a while, extracting the high resolution, the highest level of detail from the NIS, and then do the ladder approach versus the star approach. This results over here is only for extracting the level of detail from the NIS. So within the NIS, there are levels of detail, as mentioned before, the 20K, the 40K, the 80K, and the 150K. And that's without any generalization from the model. That's the level of detail in the NIS. So as we can see over here, there are 3 islands. 2 of them are in the entrance of this canal. that was totally eliminated in the rest of the level of details. And by calculating those islands distance from the mainland by mean of the near distance tool in ArcGIS, where I can calculate all the distance for all islands from the mainland and sort them in a table. So I figure out that those two islands are more than the tolerance for this scale. So as a result of the model, this is the NIS database, the level of detail for the 40K, and this is the generalized according to the model. And as we can see over here, there is a high correlation between the two levels, and those two islands were maintained. And I've used the band simplifier. There are several algorithms in ArcMap for generalizing. I've used the band simplify one for generalizing this. This is the final slide, just to show you the difference between the ladder approach to the star approach. So this is the 80K level of detail in the NIS, and this is the result of the model for generalizing using the ladder approach versus the star approach in the 80K. And that's both of them on top of each other. And here is the same for the 150. That's the NIS, and that's the two level of from the ladder and from the star. So if we zoom in for a while, that's the 80K and that's the 150. We can see that there is no different, hardly different between the two of them in the 80K, and there are a lot of different in the 150K. It seems that the ladder approach maintained more detail. So that's exactly what I'll be doing during the research, is comparing the ladder to the star and figure out the best solution and maybe use a hybrid system from both of them. That's it for the presentation. Thank you for listening. Hoping to have questions.
All right, thank you, Tamer. Yeah, I see somebody with a virtual applause. Please join me in a round of virtual applause. We need to find a better mechanism for doing this. That was good. As well, we let Tamer catch his breath for a second there. We're going to move on and start taking questions from the public right now. A couple of ways you can do that. You can put questions into the chat, and I will read them out. Or if you want to, you can just raise your hand using the reactions panel, and we'll see that and we'll call on you to ask questions. So let's start immediately. Kim Lowell has a question. Kim, you want to unmute yourself and ask your question?
Yeah, Tamer, a lot of what you're doing will necessitate you to try a generalization and see how it performs relative to another generalization. And in your talk, you focused on individual elements that we can say, yes, it worked, or no, it didn't work. And even there, you'll have to figure out a tolerance to say, here's a case where it did work, and here's a case where it didn't work. How do you combine all of those to say, here's a way of doing a generalization, and it did very well on islands, but not very well on coastlines, or something like that? Have you given thoughts to how you're going to measure something to say, not only is it good enough, or not only is it better than another way, but is it good enough relative to what we're trying to accomplish?
Yeah, thank you, Kim. That's a great question. And that's one of my main research topics, is to figure out how the model will act with each geofeature independently, and then how they interact with each other, all of them. And that's exactly what I'm trying to do in the model, in these 8 models over here. So each one of them will deal with a specific geofeature object. And then that's the question that I've just asked. Do I have to do all of that simultaneously or in sequence? So the result of each one of them will be compared, and then finally, when they interact with each other, that's the end result, where I need to compare this to the available ENCs in the area. So I hope I've answered your question. I'll be considering that during the research for sure. That's a very important one.
Yeah, thank you. That's good. And I look at the complexity of it, and I see that you have constraints that have different weights. And yeah, it's something that you'll figure out when you get there, but in what you're doing, it is quite complex. So thank you very much.
Thank you, Kim. The most challenging thing for me is to translate this constraint to a language that the system would understand, and that's what I'll be trying to do.
Yeah, great.
So we have another. Oh, sorry, Kim. Are you happy? Okay, good. So we have another question here, Tamer. Somebody with initials HKV. I'm sorry, I don't know the rest of your name. And the question is, well, first says, great job, well done, very thorough. The question then is, what do you believe is the most important of these many problems that you have identified to address? So of all the problems you're looking at, which one comes first, or which one is going to be most impactful?
Well, that's a great question as well. There are lots of problems, but I believe the inconsistency between the cells is a very important one, because that's where the mariner loses his confidence in the chart when he sees this type of inconsistency between the contours, between the depth areas, and this causes problems in the EGDIS as well. Sometimes the EGDIS will respond sluggishly or slowly, or sometimes it happens that the EGDIS might crash from something like that with the depth contour set to a safety contour, where the safety contour has been shifted, like just the example I've seen. So I believe the inconsistency is one important thing. The production time as well is very important in order to accomplish the target, especially for offices or hydrographic offices where they haven't completed their coverage yet, and there are lots of these worldwide. And for sure, for NOAA to update their or rescheme their plan, this needs a lot of time, just like what we showed. So I'm hoping that this might help on this goal.
So maybe if I can just extend that a little bit. If you're thinking about the various features that you've highlighted that you're going to be working on in Group 1 and Group 2, which do you have a feeling yet for what you think is going to be the greatest level of complexity there, or the most difficult thing to deal with there?
I think the island selection, I'm very interested in the island selection because lots of work has been done in depth generalization and sounding selection, but for island selection, I think I'll be focusing on this to figure out the best way, because as I've mentioned before, some claim that the island selection is very important in the quality of the map and how to do this in an automatic way. So I believe the land area, the island selection is going to be one of the prominent one in my model.
Okay, Glenn Rice has a question, or he says ominously, or two. So Glenn, you want to unmute and ask your question?
Sure. Yeah, the questions never end. Thank you, Brian. Great job, Tamer. Really appreciate this. This is really important work. I was curious. So I work for NOAA within the Office of Coast Survey, and one of the things that my project's been trying to build toward is the upcoming S100 standard. And it seems like a lot of what you have here is very S57 specific. And I was curious how much you'd consider the S100 model.
Well, that's another great question for sure, but the S101 has not been completed yet. That's why I've mentioned the S101, and that's another challenge for many hydrographic office to upgrade their database from the S57 to the S101. But until now, the S57 is the one that most offices are working with, and for sure to update this to the S101, that would be another. I've mentioned that before. That's another challenge, another load of work. But there's no big difference between the S101 portrayal and the S57, as far as I know. So I believe this will be compatible with both standards.
I think that is the case in a lot of, that is true in a lot of cases. But I guess the reason that I ask is specifically because if it is a standard that isn't codified yet, that this kind of work could actually help improve the S100 model specifically if you do run into things that could be changed to make your work easier, better, faster, cheaper, like all those kinds of things. So that was primarily why I was wondering if you'd considered it. The other question I had was really around the choice of your location to work. So my project specifically is building seamless bathymetry for regions. And it seemed like you're focused on the Seattle region, but the Marine Charting Division has been focused on doing rescheming a lot in the New England region, and there's been a lot of effort put in there. And so, if you were working in that region, it seems like there'd be a lot of synergy both between what I'm doing and the bathymetry you'd have available to you, or my project would make available to you, as well as the work that MCD is currently doing and kind of the processes that are already going through. So Is there a reason why you chose this location versus maybe where MCD is actively working?
To be honest with you, I've picked this area as a recommendation of one of my committee for sure. And it's as I just said, it's seamless. The coverage is very good. We have 3 layers of ENCs on top of each other over here. So that's, and the coverage, we have 3 or 4 levels of details in the NIS. So that's why I've picked this area as a study area as a start. And then I've also mentioned that this need to be tested in other areas. So maybe I will pick another one to try the model and compare both. And this is a must for sure. I'm not going to use only one area to prove the concept. I would have to do that in several areas to figure out the result and compare it to the, and I need some help for sure from others, from maybe MCD, from anyone who would like to help to compare, to send the result and compare and have how much correlation do I have between the both of them.
Great. Well, I think I'll just say the NBS project looks forward to further dialogue.
Thank you. Thank you, Chris.
Thank you.
Okay, we have another question from Giuseppe Mazzetti. He asks, to start with, or first says great presentation, and then says, what is the expected time frame of the research work that you have just presented?
Well, I'm hoping I can do that in less than 2 years, I believe. So that's my time frame according to my situation right now. Hopefully I'll be doing that in less than that. I hope that answers your question, Giuseppe.
Okay,
we really miss you. We really miss you, man.
There's a follow-up question. He also asks, I'll just read it out. How do you plan to manage the risk that improvements or optimization of your model will take several years? Meaning, I guess, meaning, you know, if it takes a while, is that a risk, and is there a way to deal with that?
I don't get the question. So what does it mean? Is it the risk to finish the research in a couple of years?
Well, no, I think that I think the intent is that if the improvements take a long time, then there's a risk that the models aren't going to get, the process isn't going to get better before it all gets done, sort of thing. I guess. I think that's maybe the intent there.
Yeah, I totally agree. People are working on that. Several people are working that because that's main interest for many hydrographic offices. So I hope I can accomplish that before someone else do it.
Okay. All right. Do we have any further questions from the audience, from the public audience? Any more raised hands or comments? All right, going once, going twice. All right, in that case, thank you all again for taking time out of your Friday, particularly at least in the US, and a long weekend, to come and listen to Tamer.